I welcome all of you to the video lecture series on computational fluid dynamics, development, application analysis. The title of this lecture is Physical Law-Based Finite Volume Method, which corresponds to the first section of the chapter titled Computational Heat Conduction, which corresponds to the chapter 5 of this companion book. So after presenting the topic 1 on introduction, topic 2 on essentials for fluid dynamics, we are into the topic 3 on computational heat conduction. And this lecture is the first lecture in a series of lecture for the computational heat conduction. And then the title of this lecture is Physical Law-Based Finite Volume. So this is the title corresponding to this lecture, Physical Law-Based Finite Volume. This slide presents the mind map of the chapter 5 of the companion book, where the title of this chapter is Computational Heat Conduction. The title of this lecture is Physical Law-Based Finite Volume Method, where basically a mathematical formulations which involves linear algebraic equations. Note that in fluid dynamics, the governing equation is a partial differential equation, but in a computational fluid dynamics, the governing equation is linear algebraic equations. So the governing equation, the mathematical formulations that we do in CFD is called as algebraic formulations. And we need to do algebraic formulations for the points which are grid points which are inside the domain, as well as we also have to do for the grid points which are at the boundary. So the physical law-based finite volume method will be presented here to obtain the linear algebraic equation for the internal grid points of the yellow circles that I had shown in the previous lectures. And in the next lecture, finite difference method will be presented for the discretization of the boundary conditions. Thereafter, I'll discuss the stability and the convergence criteria before I go into the solution methodology. So this is a topic, any product development start component by component. So note that the heat conduction is the first component that we are developing, and any development, computational development is based on certain theory, and in this theory there is some mathematical formulations which we finally implement as a solution methodology. So note that these two topics will cover the mathematical formulation which corresponds to linear algebraic formulation before we go on to the solution methodology. The solution methodology will be presented for 1D conduction and 2D conduction. Before we go into the physical law-based finite volume method or the algebraic formulations for the internal grid points or the yellow circles, let me highlight the key difference between the analytical heat conduction and computational heat conduction. In an analytical heat conduction is continuous, whereas any computational heat conduction is discrete in nature. So I'll highlight the continuous nature in analytical heat conduction and discrete nature in a computational heat conduction. Note that you have taken a course on analytical heat conduction in your undergraduate, where you start with a domain. Basically, in a Cartesian coordinate system, in a 2D case, you take a Cartesian control volume of which delta x in the x direction and delta y in the y direction. And in your analytical heat conduction course, to derive the differential equation, the governing differential equation in heat conduction, you finally apply delta x, delta y, as well as delta t, which is the time step tending to 0. So in any analytical heat conduction, you start with a domain which corresponds to a control volume of spatial width delta x and delta y, which are shown here, and a time interval delta t. So in an analytical heat conduction, you apply limits delta x tends to 0, delta y tends to 0, and delta t tends to 0. So you are considering this control volume at time step as infinity small, which corresponds to exceedingly small. Whereas in a computational course, note that the finite volume method which is presented here is different from the finite volume method which is presented in almost all the other books in CFD. All the other books in CFD start with the differential equations, whereas the finite volume method that is presented here, I have proposed it as a physical law-based finite volume method in the companion book, where the derivation of the governing linear algebraic equation start from the same control volume from which your undergraduate heat transfer course start. However, note the difference between the computational heat conduction used here. In your undergraduate course, when you have taken this width of the control volume, finally you have used delta x, delta y tending to 0. In a computational course, we will not take it to 0, but we will consider them to be finite, but it should be small enough for accurate solution. What is mean by small enough is problem dependent in any computational course. This I'll highlight later in the course. So when you consider the known variables in analytical and computational heat conduction, the known variables are basically the spatial and temporal coordinates. In 2D Cartesian coordinate system, your spatial coordinates are x and y, and temporal coordinate is t. So note that in your analytical treatment of heat conduction, you consider continuous space and time. So you consider x, y, and t as continuous, whereas in a computational course, note that we have a pixelized type of representation where we have grid point by grid point representation, and where I have highlighted that grid points are like pixels. So, and each pixel or grid point has certain x and y coordinate. So note that in computational heat conduction, the solution that we will obtain, the temperature that we will obtain in an analytical heat conduction course, like in a 1D steady state heat conduction, we have obtained analytical solution as T minus T1 divided by T2 minus T1 is equals to x by L, where T1 and T2 are the temperature at the two ends of a thin plate. So there you have obtained T as a function of x in 1D conduction. Similarly, if you consider a 2D conduction problem, so you obtain a solution which is continuous space and time. So spatial coordinate and temporal coordinate are considered continuous. Whereas in a computational course, this grid points that we represent as well as the time interval that we represent are discrete in space. The grid points are discrete in space and you have a discrete time interval. So in a 2D Cartesian coordinate system, we store the value of the x and y coordinates of the grid point, the x coordinate and y coordinate in a matrix form, where this I and j represents the running indices with or address for corresponding to an element in the matrix. Similarly, time is a one-way coordinate system. So similar to I and j as the integer value to store the address for the inner matrix. Similarly, you can store time as a 1D matrix where n is varying from 0 to, when n is equals to 0, it corresponds to the initial condition. So T0 corresponds to T is equals to 0 and T1 corresponds to delta T, when T2 corresponds to 2 delta T. So your time progresses in a discrete way from T1, which is 0, to T2 delta T, T3 2 delta T. So the time progresses 0, delta T, 2 delta T, 3 delta T, and so on. These are your discrete time. And the grid points are also discrete in space. So this slide is highlighting the key difference between analytical and computational heat conduction. And note that the difference is continuous and discrete framework. Analytical heat conduction follows a continuous framework, whereas computational heat conduction follows a discrete framework. So I'm trying to take you along. This is what you have already studied, and this is what you are about to study, you are going to study. So I'm just highlighting the similarities and dissimilarities between the analytical and computational heat conduction, so you can develop better appreciation of what is presented later on in the computational heat conduction. Now, in your undergraduate courses also, when you took this control volume, basically you apply certain conservation law. In heat conduction, you apply a conservation law which is called as energy conservation law. And I am calling the energy conservation law that you applied in your undergraduate heat transfer course as a continuous form of the conservation law. Note that the statement that you use in undergraduate heat transfer course is applicable for each and every time instant. And you have considered time as continuous. So in your undergraduate course, the statement, there are two things. One is a statement and second is a formulation. So the statement which is used for in the undergraduate heat transfer course for heat conduction while deriving the governing equation for heat conduction is rate at which, let me show you the equation. So basically the equation that is used is rate at which heat is entering plus the rate at which heat is generated minus the rate at which heat is leaving the control volume. Let us suppose this is a control volume that you are considering, arbitrary shape control volume. So the rate at which heat is entering plus the rate at which heat is generated minus the rate at which heat is leaving. This is the total heat rate at which heat is stored inside this control volume. In plus generated minus out. This is equals to rate of change of enthalpy. Note that the symbol, this curly h, curved h corresponds to the amount of enthalpy. Okay, so this is the rate basis you are using. So you are making a statement as well as this is the formulation. So note that here your statement as well as formulation is on rate basis. However, the conservation law that I will start for presenting the physical law based finite volume method, the statement that I will use is the statement that you have studied in your undergraduate course on thermodynamics. Note that energy conservation law is not only used in heat transfer course, energy conservation law is also used in thermodynamics. But the way statement of energy conservation law is presented in thermodynamics is different from the statement that is presented in heat transfer course. In a thermodynamics, as compared to heat transfer, the statement of energy conservation law says that the amount of heat which is entering plus the amount of heat which is generated minus the amount of heat which is leaving the control volume is equals to change in enthalpy. So the formulation, so this is the statement which is on amount basis. But I would like to highlight that although our statement is on amount basis, so statement is on amount basis, but note that to develop formulation, let me show you the formulation also. This is the formulation where I have taken the delta T common from all this Q. You note that here, although the statement is on the amount basis, but note that the symbols which while obtaining the mathematical formulation, the heat which is expressed here in thermodynamics, when you express Q corresponds to amount of heat, whereas in thermodynamics this Q represents rate of heat transfer. So note that although the statement was on amount basis, but to formulate the symbols which are used here I am not using a separate symbol for amount of heat, but instead I am writing the amount of heat as a product of rate of heat transfer multiplied by time interval. Note that the statement that we use in computational heat conduction, the statement is applicable for each and every time instance, whereas the statement which is presented here for a computational heat conduction is for over a certain time interval. Now, to make you understand and appreciate, let me take an example. Let's suppose if you have a measuring device, let us suppose you have a thermometer or any measuring device or pressure measuring device, any measuring instrument, when you, with respect to time, if you measure the data, whether it could be temperature variation or a pressure variation, the data which you get is not at each and every time instant. There is always a time interval between the two data that you get from a measuring instrument. So whether you do an experiment or in theory whether you do a computation, the data which you get is always discrete in nature. So for a computational heat conduction course, I had proposed that instead of using this conservation law, let us use the conservation law which is applicable over a time interval, due to the fact that in any computational course, our time is discrete in space. The data that we get is always over a time interval. I have mentioned that CFD is a subject where you create movies, where you get the picture, the data for the second picture after a certain time interval. So from the first picture of initial condition and boundary condition, I have mentioned that you get a second picture after a certain time interval. Okay, so between two pictures, there is always a time interval, which I had taken an analogy with the frame rate of the video camera. So what I mean to say is that here I am trying to present a physical law based finite volume method using a discrete math independent of continuous math. So from the beginning, when I'm proposing a conservation law, the energy conservation law, I'm making a statement which is applicable over a time interval, because this is the fact of the matter that our time instants are discrete. They are delta t, 2 delta t, 3 delta t. So let us use the energy conservation law over a time interval. So this energy conservation law is applicable to time interval between 0 to delta t, or delta t to 2 delta t, 2 delta t to 3 delta t. So always the statement which I am presenting here is applicable over a time interval. And over this time interval, when I have to represent the amount of heat which is entering, I am expressing it as a product of rate of heat transfer multiplied by time interval. Now, whenever you use this, there is always a question. Now, let me take back to your the same example. Let us suppose you have a temperature measuring device which is giving you the temperature measurement after, let us say, every 5 seconds. So the question which comes to mind, let us suppose you got the temperature at 0 second, 5 second, 10 second. Now let us suppose between you have got 0 second and 5 second. So the data which you have got at 5 second, the instrument has certain response time. It between 0 to 5, it took some time to respond. So whether you call the temperature that you obtained, which is whether that temperature is corresponding to 0 second or 1 second, if you want to represent the temperature that you have measured to a particular time instant, although the measuring instrument took 5 seconds to get you the temperature, but if you want to associate the temperature that you had measured at 5 seconds to a particular time instant, then you would wonder whether you should associate with 0 second, 1 second, 2 second, 3 second, or 4 second, or 5 second. So what I mean to say is, mathematically, when some variable is varying over a time interval, where the limit of integral is t to t plus delta t, so when some variable is varying over a time interval, mathematically we have one term which we call as time averaged value. What is time average value? This is like a one time instant representation which corresponds to the total. So note that this integral of q is the rate of heat transfer. You are doing a time integral of rate of heat transfer. So this integral is giving you the amount of heat, which is amount of heat over a time interval delta t. So if I want to express it by one time instant, which I call as mean or time average, then this is the mathematical expression which is used to represent this. So later on we will use certain approximation. Note that any computational course, when we use discrete math with respect to our, as in this case our variables are space and time. So later on, while using discrete math to derive the linear algebraic equation, we will use certain space averaging and time averaging, because space is our independent known variables, time is our unknown variables. So with respect to space and time, note that this time average is being used to represent, because note that I am trying to discretize the time. The phenomena is happening over a time interval, but by using an approximation, I want to represent it as a one time instant value. And that one time instant value, mathematically, we represent it what we call as mean or time average value. So to calculate the amount of heat which is entering on the amount of heat which is leaving, what we do is that we do some approximation which we call as, mathematically there is no, I have not right now not using the approximation. The approximation I'll use later, but what I am telling you is that to calculate the total amount of heat which is entering, I am expressing it by a time averaged amount of heat, time average rate of heat transfer multiplied by the time interval. So this is the time averaged amount of heat using the time average heat transfer rate. This is the amount of heat which is entering. This is the amount of heat which is leaving. So the amount of heat which is entering plus which is generated minus which is leaving is equals to change in enthalpy. Note that you have studied in thermodynamics that heat and work are the path functions, and enthalpy, entropy, internal energy are point functions. So we have, so when enthalpy is a point function, when we talk about the change of enthalpy, we express change of enthalpy as since it's a point function from the as a function of end states. So the change in enthalpy with respect to time, the change is represented like any point function, enthalpy at state 2, which is corresponding to T plus delta T, and minus enthalpy at T. So this is the change of enthalpy with respect to time. The final state corresponding to T plus delta T and initial state. Whereas this, the rate of heat transfer, note that with respect to time, they are like path functions. So the change of amount of heat, which we had expressed in terms of rate heat transfer, since it's a path function with respect to time, we have presented it like an integral. So I also want to highlight that in thermodynamics, note that you never use any symbol for rate of heat transfer. So note that although I am using a statement which I am borrowing from thermodynamics, where the statement is on amount basis, but note that the symbols which I am using here are the symbols that we have seen in heat transfer course. So note that I am borrowing certain thing from thermodynamics, which is the statement of energy conservation law in thermodynamics. However, while formulating, when I'm using symbols, I'm using a symbol of which corresponds to rate of heat transfer. That is introduced in heat transfer, not in thermodynamics. So I'm considering both and then giving you an expression for the rate of heat transfer as a function of enthalpy. So this is the starting point from which we will start to derive our algebraic formulation using physical law based finite value. So finally, I'll conclude this slide saying that in the physical law in your analytical heat conduction is in continuous form, and it is applicable for each and every, since it's applicable for each and every time stream. So, and in CFD, the statement that we are making is applicable over a time interval. And since it's applicable over a time interval, this I'm calling as discrete form. And in this case, you get, note that you get time derivative. Whereas in this case, you get this is like a linear algebraic form of the conservation law, energy conservation law. Here the statement as well as formulation is on a rate basis. Whereas here the statement that I had made corresponds to amount basis. Although the final formulation which I have obtained is consisting of rate of heat transfer. And if you divide this delta T, if you take this delta T from the left hand side to the right hand side, this becomes rate of change of enthalpy. The final formulation is on rate basis and the statement is on amount basis. When you compare the governing equation in analytical and computational heat conduction, you take the same control volume. In an analytical heat conduction, you apply delta X, delta Y, delta T tends to 0. So you consider an infinitesimal control volume. And this is the governing equation that you derive for heat conduction, and steady state heat conduction with volumetric heat generation. Whereas later on I will show you the complete derivation, but to present in an overall generic form, in a physical law based finite value method, we use discrete math based approximated linear algebraic equations. So note that here I will present discrete math independent of continuous math, because from the very beginning, like in earlier slide I had introduced time averaged, we are not presenting any variable as a continuous variable when we start from the control volume. So we take a finite control volume instead of infinitesimal control volume in differential formulation for an algebraic formulation. And finally, we obtain an algebraic formula. Later on, I'll show you the detailed derivation. This is shown for an expressive method, where it turns out that for any internal grid point, which I had shown earlier like yellow circle, P, we got an algebraic equation as shown here. It's a Tp is a function of Te, Tw, Tn, and Ts. So it is function of its north, south, east, and west neighbor. So we in our algebraic formulations, we obtain expression of a grid point in terms of nearest neighbors, the four nearest neighbor, north, south, east, west, not the other neighbors. So let us suppose if you have a domain with 25 yellow circles or internal grid point, for each point you obtain an algebraic formulation which is function of its four neighbors, not all the remaining 24 yellow circles in the domain. Now, if you compare after the governing equations, I started with the domain, the known variable, the physical law in the previous slide. And this slide, I'm showing you the governing equation, initial condition, boundary condition, and then I'll also show you the solution. So the governing equation, here you obtain differential equation. Here I'm setting computational conduction, we will obtain a system of algebraic equation. If you see initial condition and boundary condition, your initial condition, which is corresponding to time t is equals to 0. This initial condition is applicable for x and y which are continuous in space. So this initial condition is continuous. Whereas in a computational heat conduction, our initial condition is also grid point by grid point. So we have different grid point where these are the x coordinate and y coordinate. So our initial condition is also discrete in nature. In your analytical heat conduction, the boundary condition, there are two standard boundary conditions which I had mentioned. Dirichlet boundary conditions where the temperature on a surface is known. So temperature is given to you, or if it's a non-Dirichlet boundary condition, then you have a first derivative. I've mentioned you can have either insulated or constant heat flux or a convective boundary condition, where in a non-Dirichlet boundary condition, you get a linear combination of the value of the temperature and a normal temperature gradient on any surface. So in a analytical heat conduction, note that your boundary conditions are continuous in space, whereas in a computational heat conduction, corresponding to each boundary grid point, which I had shown by blue circle in my previous slides while showing you the grid generation, separate linear algebraic equation is obtained for each boundary condition with finite difference method for the first derivative. So note that the boundary condition is implemented, initial condition as well as boundary conditions are implemented in a discrete form in a computational heat conductions, whereas they are applied continuous space in time in an analytical heat conduction. Even if you see the solution or in an analytical heat conduction is a functional form. Like as I mentioned, in 1D steady state heat conduction over a thin plate, you get a formula T minus T1 divided by T2 minus T1 is equals to x by x. So T as a function of x. So you get a function as a solution. So which I had mentioned earlier, that when you get a function as a solution, you can substitute any x, any y, any time to obtain the solution for temperature. So I have said that analytical heat conduction, you can consider it like you can give, it's like an infinite resolution video camera to get a movie for temperature distribution. Whereas in computational heat conduction, your solution is not for each and every point. Our solution is at certain points which we have obtained through grid generations. So our solution here it is shown in terms of discrete x and y values and discrete time. So we have what we call as finite resolution virtual video camera. Finally, I would like to highlight that in undergraduate course you derive only one formula, like T minus T1 divided by T2 minus T1 is equals to x by L. You derive only one formula and that you use calculator to solve it. Okay, so you have one equation for calculation. Whereas in a computational heat conduction also, note that we here also derive only one equation. We derive one equation means what I mean is that although in a you may have millions of internal grid point, but note that we obtain the algebraic formulation for one of the internal grid points, and that equation we write it in a indicial form or matrix form. So note that in just to give you an idea, let us suppose you have an equation z is equals to x into y. So in an analytical course, you have one value of x and one value of y. Whereas in a computational course, we also derive one formula. Let us suppose we have derived the same formula z is equals to x into y, but the difference is now this x and y and the known values, they are not one value. they are multi-value, and we, let us say in a 2D problem, we store it as a 2D matrix, and so this is corresponding to xi comma j and yi comma j. So this is, since it's a multi-values and it is stored in a data structure of 2D matrix. So here also we derive one formula, but we express it in an indicial form. So note that the effort which is required in deriving, or the math which is required, is of the almost same level, because in both the cases we derive one equation. Although and then we take this equation and we take it to because this equation is very I would say tailored towards the recursive computations. So basically we write a small program for I varying from, there will be a range in which I will be varying, which corresponds to the size of the matrix. There will be a range of j values. So we use loops typically to calculate this z as a function of x and y. So this is used in a calculation for a single valued problem, and it's a multi-valued problem, and this is tailored towards the recursive computation. So we use loops and we write a small program and do computations. The simplest form of the grid generation, which is called as uniform grid generation for a Cartesian coordinate system, is presented here. Suppose we have a square domain of length L1 in x direction, L2 in the y directions. So let's suppose this is the simplest form of the grid generation is that we draw equispaced vertical lines and equispaced horizontal lines as shown here. So note that by drawing these lines, we have divided this. Let us suppose it's a heat conduction problem. It's a square plate. Then we have divided into 25 small regions, or we call as 25 control volumes. And these are we locate the grid points or pixels at the centroid of each control volume. And note that these points are inside the domain. These are represented here by yellow circle, and they are called as internal grid points. Note that the physical law of finite volume method, which is the title of this lecture, will lead you to linear algebraic equation for this internal grid points or yellow circles. In the next lecture, I will show you the linear algebraic equation that we obtain for boundary conditions for these boundary grid points, which are shown by blue circles. I started with left wall, then I moved into bottom wall. This is the right wall, and this is the top wall. These are the grid points at the various walls, and we have a certain specific boundary conditions. We will obtain algebraic formulations for this blue circle or boundary grid points using finite difference method in the next lecture. This lecture we will obtain the linear algebraic equations for these yellow circles or internal grid points. And this I and j are what we call as running indices, because we store the data for the x coordinate, y coordinate, and temperature in a 2D matrix. So these are the running indices. Note that when I say I is varying from this, I is equals to 1, 2, 3, 4, 5, 6, and 7. So we have total 7 points, 5 yellow circle and 2 blue circles. Total 7 points in the x direction. Similarly, you have 7 points in the y direction. 1, 2, 3, 4, 5, 6, and 7. However, note that there are 7 points, but how many divisions we are making? We are making 5 divisions. So later on, when I will show you, when we obtain the width of the control volume. Note that this is a uniform control volume. All the control volume are of equal size. So the delta x, the width in the x direction, will be obtained by, like in this case, it will be L1 divided by 5. Whereas if I want to write a general expression, note that I max is 7. So when I want to calculate delta x will be L1 divided by I max minus 2, 7 minus 2, which is 5. So for any value of I max, later on I will show you, when we calculate delta x is equals to L1 divided by I max minus 2, and similarly delta y will be L2 divided by J max minus 2. This is a computational stencil where later on I will show you derivation that the temperature at a particular point is function of its north, south, east, west neighbor, and it is not function of the other yellow circles or other neighbors. This blue circle, as I had mentioned, this is corresponding to the running indices. I is equals to 1 is the left wall, I is equals to I max is the right wall, and j is varying from 2 to j max minus 1, 2 to 6, which is 5 points as shown here. J is equals to 1 is the bottom wall, and j is equals to j max is the top wall. And I is varying from 2 to 6 again. So they have 2 to 6 means 5 blue circle on the bottom wall and 5 on the top wall. So I'm showing you the boundary grid point, their running indices. The yellow circle, if you see carefully, there are two types of yellow circles. There are certain yellow circles whose in the circumference, the black boundary which I had drawn are much thicker as compared to this ones. You can see here the black boundary line is much thicker as compared to this. This I will call it as a border grid points. Why they are called as border grid points? The yellow circles with a thicker boundary, these are called as border. Okay, let me show you. I am saying that these are border control volumes, and these are the remaining circle I am calling as interior control volumes, and both of them together I'll call as internal control volumes. So the yellow circles I'm using three words: internal, interior, and border. Now what is border? Any yellow circle whose one of the immediate neighbor, east, west, north, south. If it is a blue circle, then I am calling it as a border, because this is like the boundary, and this is one of it. This neighbor is boundary grid point. So this is sitting at the border. Okay, so this I am calling it as a border because this I classified because later on when we implement for computer programming, this classification helps in better understanding of the formulations. Just to give you an idea, later on I will show you that we need to calculate one geometrical parameter, like what is the distance between two consecutive circles. Like what if you see the distance between these two circles as I move from left to right, it is delta x by 2. So the border grid point, this I'll call it as a left border grid point. This I'll call it as a right border grid point. This I'll call as a bottom border grid point, and this I'll call as top border grid point. For the left border grid point, if you take the distance between the nearest neighbor, here you will see this is delta x by 2. And so this I will later on I will show you. For the border grid point, with one of the neighbor, the spacing is delta x by 2. Whereas if you consider this grid point, if you take its spacing from the nearest neighbor, north, south, east, west, you will see all from between all of this. With west it is delta x, with east it is delta e. For north and south neighbor, the distance between two consecutive yellow circle, this distance is delta y, this distance is also delta y. Whereas for any border control volume, with north, south, east, for this border control volume, this is delta y, this is delta y, this is delta x, but here it is delta x by 2. So as I mentioned in my previous slide, that after grid generation, we calculate certain geometrical parameters. Note that later on in our formulation, these geometrical parameters appears as the coefficient of the linear algebraic equation. What are the coefficient? Like if you have a linear algebraic equation 3x plus 4y is equals to 9. So this 3 and 4 are the coefficient of x and y respectively. So the coefficient of linear algebraic equation that we derive from physical law based finite volume method consists of two things. One is the geometrical parameters that I am presenting here. The geometrical parameters corresponds to the surface area of the control volume, volume of the control volume, and the distance between a representative grid point and its nearest east, west, south, north, south neighbor. So after you do a grid generation, such as in the previous slide, I had shown that for a square plate, we have 5 divisions and there were 7 points. So first we calculate the width of the control volume, delta x and delta y. And as I had mentioned earlier, we calculate delta x, delta y using a general formula. In the previous slide, I max was 7, J max was 7, and 7 minus 2, which is equal to 5. So basically L1 and L2, we are dividing by 5 corresponding to the previous grid generation that I had shown. So the general expression, this is the general expression to calculate delta x, delta y. If you know L1, L2, and as a user, you decide how many number of points you want to distribute. In the previous slide, I have taken I max J max is equals to 7. Once you know this delta x, delta y, the surface area and volume of the control volume. Now, what are the surface area? This is the left surface or west surface. This is the right surface or east surface. This is the bottom or the south, and this is the top or north surface. So for the vertical surfaces, you can see that the width of the control volume is delta y, and for horizontal surfaces, the width of the surface area is delta x. So these are the various surfaces: east, west, north, and south. So the surface area of east and west surfaces are vertical surfaces. The surface area of east and west is delta y. The north and south are horizontal surfaces, and its surface area is delta x, as shown. Now the volume of this Cartesian control volume is delta x into delta y. Along with the surface area and volume, we also need certain distances between, as I mentioned earlier, between any grid point with its adjoining east, west, north, south. These are the distances in the x direction for any representative grid point P. If you want its distance from capital E, it is on the east face, so we denote it as delta x E. This distance is in the x direction. This distance we denote it as delta x W. Similarly, the distance of this representative grid point P with north and south is represented by delta y and delta ys. In the next slide, I will show you the expression for this distance of a representative grid points from its nearest east, west, north, south neighbors. Distance between a control volume cell center and its neighbors, east, west, north, south, which is shown here. Delta xw, delta xe is equals to delta x for all the control volume, except there are some exceptions which I'll talk later. And delta y s and delta is equal to delta y n is equals to delta y. For the left border controller, now let me explain you. These are all border control volume. What I'm telling is, if you take this point, its delta x w is this, delta x is this, delta y n is this, delta y s is this. All these distances, this is delta x, this is delta x, this is delta y, and this is delta y as shown here. However, if you consider the certain border, left border, right border, bottom border, and top border control volume I have shown. So for the left border, the delta x w, if you see, when I say w means the distance of this border grid point from its west neighbor. Now what are the west neighbor? All these are these blue grid points. Now the distance between delta x w here is delta x by 2. So delta x w is delta x by 2. Whereas when you go to the right border, now for the right border, delta x w is delta x, but now in this case delta x e, one of its neighbor is on the east side, the boundary grid point. Delta x e is delta x by 2. Similarly, for the south, for the bottom and top border grid point, for the bottom border control volumes, delta ys is equals to delta y by 2, and for top border control volumes, delta y is equals to delta y by 2. Later on, this distances we will use in the solution methodology. So note that I had mentioned the geometrical parameters. After we do a grid generation, we calculate certain geometrical parameters like surface area of the control volumes, the volumes of the control volume, and the distance of a control volume, cell center or centroid from its east, west, north, south neighbor. These distances are the third geometrical parameter. This geometrical parameters appears as the coefficient of the linear algebraic equations, along with the thermophysical properties. So I started with key differences between analytical and heat conduction. Then I introduced the grid generation, the Cartesian grid generation. Note that this we are into the part 2 of this lecture series corresponding to computational fluid dynamics for a Cartesian geometry. So here you learn to develop a computer code or a software for Cartesian geometry problem. So that's why here I have shown you the grid generation for a Cartesian domain. So after this, let us go ahead and I will present the physical law based finite volume method for heat conduction. So here we will start with the conservation law, energy conservation law, and then we'll go to the algebraic formulation. Thereafter, we'll use certain approximation and get an approximate algebraic formulation. So note that the final end of our mathematical formulation is the approximated linear algebraic formulations. As I mentioned earlier, there are two forms of energy conservation law: continuous form, which you have studied in your undergraduate course, which is applicable for each and every time instant. There is another form which you studied in your thermodynamics course, where everything is about on the amount basis. Here it is on the rate basis. And this statement is applicable over a time interval. So in the heat transfer course, the statement that we have used is the rate at which conducted thermal energy enters a control volume plus the rate at which thermal energy is generated within a control volume minus the rate at which the conducted thermal energy leaves the control volume must be equal to rate of increase of enthalpy stored within the control volume, which is mathematically expressed in this form. Whereas in thermodynamics, you have the statement that you have used involves amount. Okay. However, I am borrowed the statement from thermodynamics, but note that the formulation that I am doing, for which the symbols I am using, is corresponding to a term which involves a rate of heat transfer. So I have written the amount of heat as a product of rate of heat transfer and time interval. And the rate of heat transfer, I am representing it by a time averaged value. So the statement which is being used here is the amount of conducted thermal energy that enters a control volume plus the amount of thermal energy that is generated within a control volume minus the amount of conducted energy that leaves the control volume must be equal to amount of increase. Note the highlighted word rate in this statement and amount on this statement. This leads to a mathematical formulation as shown here, where I have mentioned what is meant by mean. So we are expressing the amount by a one-time instant value of the rate of heat transfer, which is going in and out here. Now, I started with the energy conservation law. Now I'll show you the algebraic formulations. So note that here we are starting with the physical law as compared to all the other books in CFD which start with the differential equation law. So this finite volume method start with the same picture and which you have used in your undergraduate course. And we apply this energy conservation law over a time interval. We will use two different approximations and derive the linear algebraic equations. So to take you along, let us suppose this is the grid which you have generated, and this is a representative control volume that I am showing you separately, where this is the grid point P and east, west, north, south neighbor. And this is the rate of heat transfer. This is the width of the control volume, delta x in the x direction, delta y in the y direction. So in our energy conservation law, there is change in enthalpy and rate of heat generation. Now this enthalpy I have mentioned in my previous topic, that if you like in thermodynamics, you know that there are two types of properties: intensive properties and extensive properties. Similarly, I have mentioned if you want to learn CFD, the essentials of fluid dynamics and heat transfer is, while applying the conservation laws, there are two types of terms which are depending on the volume of the control volume and the terms which are depending on the surface area of the control volume. So here for heat conduction, I'll highlight three terms: enthalpy, heat generation, and the conduction heat transfer rate. Now these three terms I have mentioned earlier. There are two terms which depends on volume. Like enthalpy consists of mass. Mass depends on volume. So enthalpy depends on volume, so it's a volumetric term. So if you want to calculate enthalpy inside a control volume, enthalpy varies at various points in the control volume because it depends on the volume. So enthalpy varies all over the volume. Whereas if you talk of the conduction heat transfer rate, you express it at the surface area of the control volume. You have Qx plus delta x, Qy plus delta y. So this depends on the surface area. So here what I'm saying is the change in enthalpy it's like, as I mentioned, enthalpy is a point function. The change of enthalpy with respect to time, this is the final state and this is the initial state. So with respect to time, it is expressed like this. Now any enthalpy I have mentioned, I can write it as a product of enthalpy with a bar multiplied by volume. Heat generation also, I am writing it as a bar. What is this bar? This bar is a volumetric term. It's a per unit volume. When I use H with a bar, what I mean is enthalpy per unit volume. When I use heat generation bar, what I mean is rate of heat generation per unit volume. So what I'm expressing here is, note that I'm expressing, in the earlier case, I was expressing the time integral by one time instant value. Here it is a volume integral of enthalpy, which I am expressing it by one point in a volume. Okay, so I am expressing, so for time I have used a superscript mean. For space I am using a subscript. This volumetric term I am using a subscript average at a volume. So while applying a discrete math, note that mathematically we have terms which we call as for one time instant representation. When something is varying over a time interval, when I want to express it for one time instant, we use a term which is called as time average. When I want to express some variable which is varying in space, then I have mathematically I have a term which I call as space averaged. Here the space is a volume on which this variable enthalpy is varying. So I'm calling it as a volume averaged for the enthalpy and heat generation. Whereas later on I'll show you also for this rate of heat transfer. This rate of heat transfer involves, it acts on a surface, and the rate of heat transfer per unit area, this capital Q per unit area, when we want to represent, we represent it as a small q. So here the over bar is a volumetric term. When from capital letter to when I'm showing as a small letter, I mean it's a per unit area term. So small q is capital Q divided by A, area. So here this is Qx, this is the rate of heat transfer on surface X, this is the rate of heat transfer on X plus delta X, this is at Y, this is at Y plus delta. So for volumetric term, I have expressed the per unit volume term by volume average multiplied by delta volume of the control volume. For the rate of heat transfer on various surfaces, I am expressing it as a conduction flux. So this conduction flux Qx, if you consider at X plus delta X, note that there are various points on this surface, and it is varying on this vertical line. So on this vertical line, it's an integral of Qx dy, because on this surface the y coordinate is varying in a 2D problem. Surface in a 2D is represented by a line. This is a vertical line. Whereas if you consider Qx, sorry, Qy here, the Qy is varying with respect to x. So here is the integral of capital Q is equals to integral of small q dx. So the variation of the Qx on this vertical line is expressed by one point, and that point is called as surface averaged value. So note that for volumetric term, I am introducing a volume averaged, and for a flux term, I am introducing surface average. I have already introduced what is time averaged in my earlier slide. So note that in any computational course, note that we are not using continuous math. We are using a discrete math. Now to use a discrete math, I have to break the continuous definition. Now to break the continuous definition, well, let us suppose this volumetric, this enthalpy is varying point to point in a volume. I am trying to express it here by one time instant, because when I want to have a discrete representation, I want one point in the volume for enthalpy and heat generation, and I want one point on a surface for the flux term, conduction heat flux here. So we are using mathematically surface averaged for flux term, and we are expressing this qx plus delta x. I'm here expressing as heat flux. Note that for small q I'm using two subscript. Although I'm using two subscript, but note that this is not a second order tensor. The first subscript represents the direction of the flux. So the first subscript, note that for vertical surface it is qx, For a horizontal surfaces, this is Qy. Whereas the second subscript is basically what it is representing is the surface average or average value of this Qx at x plus delta x. This is the average value of Qx at the surface x. This is the average value of Qy. This is the Qy, average value of Qy at surface y. This is the Qy whose surface average value at y plus delta y is presented here. Okay, so this way I'm using a symbolic representation of discrete math-based representation of the volumetric and the flux term that are involved in heat conduction. Note that till now I have not used any approximation. So I will show you the algebraic formulation without any approximation to begin with. Then I will show you the two approximation, and then we will use those approximation where we will replace this average at x, average at volume with certain 1 point values and obtain the final approximated linear algebraic equations. So the physical law based finite volume method, I had mentioned the change in enthalpy and enthalpy at T plus delta T. And basically, mathematically, you can express it as the, like in thermodynamics, you have intensive and extensive properties. What is intensive and extensive properties? Intensive properties independent of mass. Okay. So similarly, I can say if I want a term independent of enthalpy, independent of volume. So if you see H bar or Q bar, they are independent of volume. Similarly, if I want a term which is independent of surface area. So if I talk of flux term, any heat flux, since they are term per unit surface area, they are independent of the. Okay, so I am expressing the per unit volume and per unit area term as an integrand. So for volumetric term, I am doing a volume integral, and for a flux term, I am doing a surface integral. Note that in a 2D, a surface is a line. That's why I am showing you a line integral. Whereas, and in a 2D case, the volume integral is basically, it involves double integral based representation. And here for the control volume, when I have to show you the limits of the integrals, because for Qx, we have to do, to calculate capital Qx from small qx, I have to show you capital Qx, it will be an integral of small qx dy, where for let us suppose on this surface, the limit will be y at SE. I'm showing you the corner. This corner I'm calling as northeast corner, this corner I'm calling as southeast corner. So for x plus delta x, Qx at x plus delta x, the conduction flux in the x direction on a surface x plus delta x, if I have to show it here, then basically I have to show the limits of the integral as y coordinate of SE minus y coordinate of NE as shown here. Okay, so I am showing the, so this will give you the total conduction heat transfer rate from the east surface, from the right surface. This is the rate at which it is entering the left surface. This is the rate at which it is leaving from the right surface. This is the rate at which it is entering from the bottom surface. This is the rate at which it is leaving from the right surface. This is the total heat which is gained by conduction. So this is the total heat gained by conduction. This is the change in enthalpy, which I am expressing it as a volume integral, where the integrand corresponds to the overbar term, which corresponds to per unit volume term. Okay, whereas conduction heat transfer rate, I am expressing it as an integral of surface integral for 2D line integral of conduction flux terms. So this is the total amount of heat which is gained by conduction. This is the total amount of heat which is gained by volumetric generation. Note that a volumetric heat generation is also a volumetric term. It is also a function of the various points in the volume, and it is expressed here as volumetric. But for most of the real world problem, the heat generation do not vary with respect to different points in a volume. So it comes out of the integral, and it's written as Q bar heat generation into delta Vp as shown here. So using this 1 point representation for volumetric term and 1 point surface representation, which I'm calling it average at phase. So I will show you that the final expression, this delta T, I can take it from the right hand side to the left hand side, and this I can replace it by 1 point representation, where I represent this as shown here. This I'm this I'm representing it. It's not an approximation. This is equal to the volume average 1 point representation multiplied by volume. So when I substitute this, and for the enthalpies, I get an expression like this. Whereas this total heat rate at which heat is gained by conduction heat transfer is when I express each of these integrals by the surface average value. So what I'm trying to say is that this I will write it as shown here is, maybe I had shown this in my previous slide also. This I'll write as Qx average at x plus delta x, which is shown here. Okay, this I will write it as Qx at average at x. So this integral I have a formula which I'm using. So this is expressed as this is expressed as this as this, and so on. So this is the final this till now I have not used any approximation. This is an algebraic formulation where I'm just using a mathematical definition, what is called as surface average and volume average, and I'm trying to represent the volume wise variation of a volumetric term and surface wise variation of a flux term by a 1-point representation. That 1-point representation in a volume, I am using a mathematical definition which is called as volume average. For a flux term, I'm using a definition which is called a surface average. So I am basically getting an algebraic formulation without any approximation till now, where I've expressed, instead of integral variation, volume integral and surface integral, I'm representing it by 1-point representation corresponding to volume average and surface average. In the next slide, I will show you the approximations where we will replace this average at volume, average at surface by a certain specific pixel or grid point values, and finally obtain the approximated linear equations. Okay, so the earlier slide, I have just used some mathematical definitions. I have not shown you any approximations. Now I will show you approximations. Mainly I will show you 2 approximations. First approximation and second approximation. And using this approximation, finally we will obtain approximated algebraic formulations. Okay, so for I have mentioned that now the time has come, I have to make a decision. The decision is, let us suppose, what is this? This is Qx, and I mathematically on a surface, although this Qx is varying point to point on a surface, but mathematically I have expressed it by 1 point, which I'm calling it as a surface average value. So if I ask you which is the best point to represent the conduction heat flux on this surface, before this let me first go to the volumetric term. I'll come back to this little later. Let us suppose you consider the volumetric enthalpy. Now volumetric enthalpy is what? Enthalpy is mass into specific and into temperature. What I mean by volumetric enthalpy, you divide it by mass. Okay, so sorry, you divide it by volume. So mass, specific heat, temperature, if you divide by volume, mass per unit volume will give you density. So this h bar is rho into Cp into T. Now for a solid surface, for most of the cases, rho and Cp does not vary in the volume. So what varies in a solid mostly is temperature. So the temperature is varying from point to point in this volume, and that is why the enthalpy is varying. So if I want to ask you that which is the best point to represent the enthalpy in this control volume, then intuitively we can think of that the best point, you may call it center, or to be mathematically more correct, centroid. Okay, so this is, so here we have made a decision that this average at volume, now the time has come that we have to associate a pixel or a grid point corresponding to this mathematical definition. And that is what makes it approximate. Note that this is not equal, this is approximate. Earlier I had always shown equal using certain mathematical definitions, but here I have to make a decision, because mathematically, when you want to solve it, you need some pixelized representation. So the approximation is doing what? It is basically converting those mathematical definition of average at volume, average at surface to certain pixelized or grid pointer representation. The first approximation for a volumetric term is we are expressing by the value of this volumetric term, which is volumetric enthalpy and volumetric heat generation, by its value at the centroid, which is represented here by yellow circles. Okay. The second thing is this flux terms for the conduction fluxes. So this for conduction fluxes, which is the best point on the surface? That's the answer we will need. Like the answer is very similar to which is the best point in a volume. In a volume, you said it's a centroid. Similarly, for a surface also, you expect that the centroid should be the best point to have a best 1 point representation. So the second approximation, what we do is that this average at x plus delta x, we replace it by small e, which is like a pixel for qx, as shown here. This is like pixel for qx. This is the qxe. This is qxw. This is qyn. This is qys. So these are the approximate representation where we have replaced this mathematical average at x plus delta x, average value of qx at x plus delta x. Here this is average value of qy at y plus delta y, which is a surface. Okay, we are representing it y plus delta y by the north. So basically we are converting this 1 point mathematical definition by certain symbols here, which is shown here. For the centroid of volume, I have shown you circles, which is like a pixel for temperature. The green square that I am showing you, it is like pixels for qx. The red inverted triangle that I am showing you, it is like pixels or grid points for qy. So with this mathematical definitions, in the first approximation, for space, we are breaking the space, the volume and the surface area by taking the 1 point at the centroid of the surface area and volume, and that is what we call as first approximation. Whenever you use a discrete map, you have to break the continuity, and this is how we are breaking the continuity, by using an approximation which mathematically is a second order accurate approximation. As far as time average is concerned, note that other than the subscript, there is also a superscript for this heat fluxes. And we also need to decide time average value. In the time average representation, there are 3 possibilities and there are 3 methods associated with it. Like if you want to represent the value of heat flux qx at x plus delta x by the value at previous time instant, then this is called as an explicit method. So what you're basically saying is, over a time interval 0 to delta t, to calculate the temperature at Tn plus 1. So let us say, like we always have, as I mentioned earlier, that in CFD we always have data from the previous picture. Like when we start, we have the first picture from initial condition and boundary condition. Using the data for the first picture, we obtain the data for second picture. So in an explicit method, the assumption that is made is, between any time instant between t to t plus delta t, we assume that between t to the over the time interval delta t, we are assuming that the heat fluxes we are taking from previous time instant, and at t the heat flux is suddenly changing to t plus delta t. Whereas when we assume the time average value from, like to give you an example, when I asked you that question, that let us suppose from a temperature measuring device, you measure a temperature after every 5 seconds. So I have asked you, you would like, if I ask you that associate this temperature that you got at 5 seconds, but the measuring instrument has certain response. So although it gave you data at 5 seconds, but between 0 to 5 seconds, it was processing. So if I asked you that which is the time instant you would like to associate it. So this explicit method is like you're saying that I would like to associate to 0 seconds. This implicit method is like you're saying that you would like to associate the data which you got at 5 seconds to 5 seconds. Whereas this Crank-Nicolson is what is doing, it is taking the mean of the two, which is 0 plus 5 divided by 2. Which is saying you would like to associate that data as the temperature for time is equals to 2.5 seconds. Okay, so it is basically we are approximating the time average value which you have got over a certain time interval. If you associate it with the initial time then it is called as explicit method. If you associate with the final time, it becomes an implicit method. And if you take the mean of the two, it is called as Crank-Nicolson method. Note that mathematically, in the previous slide, when I talked about this average at volume, so there is this mathematically, these are called as stepwise variation. And just to give you an idea, between you have a control volume here, there's another control volume here. Now, when you use this approximation, what you are saying is that like in this case, it will be a temperature. Temperature, the temperature is varying. There will be a step change in the temperature from this control volume to the next control volume. Similarly, if you talk of the heat fluxes, you are representing it by one point value. So if you consider another adjoining surface which is on this because if you increase this vertical line, it will correspond to a vertical surface for the north control volume. So if you consider heat flux from one control volume to the another adjoining control volume, the Qx at x plus delta x, it's a stepwise variation. Even this explicit implicit method, they are changed corresponding to a stepwise variation. Whereas this Crank-Nicolson, it's like a centroid in time that you are using. So mathematically, we express it by a superscript chi, where if chi is equals to n corresponds to the previous time step, n plus 1 corresponds to the new time step. So this n is like t is equals, this is time instant t, n plus 1 is like time is equals to t plus delta t. Okay, so we have three different methods corresponding to the time averaging. So in the previous slide, I had shown you first approximation for the space averaging. In this slide, I am showing you the first approximation for the time averaging. Other than the first approximation, we need second approximation for conduction heat fluxes, because finally you want to obtain expression in terms of temperature. And in heat transfer, you've studied that there is a relationship between the heat fluxes and the temperature, which comes from Fourier law of heat conduction. So the second approximation that I am representing here basically corresponds to discrete or algebraic representation of conduction heat fluxes. Now, to get an algebraic representation of, let us suppose, Qx on this surface, I need to calculate dt by dx at this green pixels. So at this green pixels, if I want dt by dx, basically to calculate dt by dx, you draw a horizontal line. If you draw a horizontal line, it is intersecting these two yellow circles. So one of the simplest idea is, let us suppose you want to calculate temperature here, and let us suppose temperature here is 100, here temperature is 0, and let us suppose the distance between these two yellow circles is 1 meter. So one of the simplest idea which comes to mind is, to calculate dt by dx here, you take 100 minus 0 divided by 1. So that is the approximation we use. So to calculate temperature here, dt by dx at small e will be T capital E minus T capital P divided by delta x, which is shown here. So this is, note that this is not the exact representation, it's an approximate representation. This is a second order central difference scheme, corresponding to which we have discretized the first derivative at the centroid of the surface area. This I had shown you for this surface. Similarly, for west surface, it will be P minus W divided by the distance of P minus W. For north, it will be N minus P, which is shown here. For south, it will be P minus S, which is shown here. So this is second approximation is a algebraic or representation of the Fourier law of heat conduction. Note that here, mathematically, this approximation is, you are assuming a linear variation between two consecutive yellow circles. So between these two yellow circles, using linear approximation. Here between P and W, you are using again another linear variation. But at P, there are two linear variations. One linear variation between P and W, another linear variation between P and E. But there is no continuity in between the two. So this approximation is mathematically called as piecewise linear approximation. So the final approximated algebraic formulations that you get for unsteady term, the change in enthalpy that you have calculated, I have mentioned that if you divide the enthalpy, this over bar is dividing by volume, then it becomes mass per unit volume. So you get a product of density, specific heat, and temperature. And temperature average at volume, we are representing it by this pixel value P. So instead of average at volume, now this becomes temperature at P. And to calculate enthalpy at n+1, which is a new time step, it is Tp at n+1 minus Tpn. So finally, this term in the numerator represents the change of enthalpy with respect to time. Enthalpy is a point function, which is where this rho, Cp, they are common. They do not vary in a volume. And this is the volume of the control volume, delta x and into delta y. This volume multiplied by density is mass into specific heat, into the change of temperature between two time instants. So this gives you the change in enthalpy. And so on the right hand side, you have a delta T term, which I have taken it to the left hand side. This represents an algebraic representation of rate of change of enthalpy. Here note that we have used only one approximation where we have discrete one-point representation of spatial variation of volumetric enthalpy at any time instant t and t plus delta t. Whereas in conduction, we have to calculate net mean conduction heat transfer rate entering at control volume. We have, for the first approximation, for volumetric, we only need 1 point representation in space. Whereas for heat flux, we not only need 1 point for space, we also need 1 point for temporal variation of conduction heat fluxes, because we also have a superscript here for conduction fluxes, because conduction, the heat considered is a path function, whereas the enthalpy here is a point function. So since Q is a path function, so there is a superscript with respect to time, which also comes in. So this time average value I have mentioned. Right now I'm showing it as a chi, but when you take chi is equals to n+1 and n plus r, these are the three different methods which I have mentioned. And there is a second approximation corresponding to the piecewise linear approximation to obtain the Fourier law of heat conduction in an algebraic form. So the first approximation, this is the second approximation. Volumetric heat generation. For most of the cases, even you don't need this, because most of the cases, the enthalpy, if it is volumetric heat generation is not varying in a volume, that you don't even need this. But in a more general case, if the heat generation is varying within the volume, then what is being suggested is that you take the heat generation for each control volume corresponding to the centroid of the control volume. The point to note here is, for the volumetric term, you have only one approximation, the first approximation. Whereas for the flux term corresponding to the conduction, here you also need a second approximation. So this is I've shown you by after first approximation, this is the algebraic equation that you obtain, where if you substitute this heat fluxes by Fourier law of heat conduction algebraic representation, then you get this equation, which is an algebraic equation. Note that finally we have obtained linear algebraic equation for all terms. Note that this is an approximated linear algebraic formulations after substituting the approximation to the original proposition, where this is the unstudied term, this is the conduction term, and this is the heat generation or a source term. When you derive in your undergraduate course, note that this equation is analogous to rho Cp del capital T by del small t is equals to del Qx by del x plus del Qy by del y plus Q bar. Okay, and in the second step, in the differential formulation, when you substitute Qx equals to minus k by dtx and Q by is equals to minus k by dt by dy, you got equation. This equation is analogous to rho Cp del capital T by del small t is equals to k del square T by del x square plus k del square T by del y square plus Q generation. So in your undergraduate differential formulation also, note that you first get a derivative for Q as a vector, del y del x of Qx plus del y del y of Qy. And later on, when you substitute Fourier law of heat conduction, in the second step, you get differential equation for temperature. So analogously, this is an algebraic equation in terms of Qx. This is an algebraic equation after applying Fourier law of heat conduction in terms of temperature. Now finally, before I end, I will show you two different forms of the algebraic formulation. The flux form that is shown here, it is obtained after the first and second approximation. It is shown separately. So in the flux, basically what I'm showing is this algebraic formulation which I'm writing not in terms of temperature, but I'm writing in terms of conduction heat fluxes, where the Qx and Qy I'm writing separately. This I am calling it as a flux form. Later on, I'll present what we call as flux-based solution methodology. For a beginner in programming, I felt that this form is easier to understand and appreciate. So that's why I have introduced this flux form. Although all the books use only one form, which I'll present in the later slide, which is like coefficient of linear algebraic equation form. So in almost all the books in CFD, they finally write the equation in terms of temperature that I'll be showing you here, where I have mentioned that this Q conduction can be expressed at this. Now this temperature chi, as I mentioned, it could be, this is n for explicit, n plus 1 for implicit, and n plus half for Crank-Nicolson. So if you substitute the temperature, this TE, TP, TW, TN, TS, as right now all of them have a superscript chi. So if you, let us suppose for TP chi, if I substitute as lambda TP n plus 1 plus 1 minus lambda TP n. And similarly for the other neighbors, east, west, north, south. Then in the next slide, I will show you. So if I substitute all these chi values in terms of lambda, n plus 1 and n, and then substitute this Q conduction here, and then if I do the algebraic manipulation, so after substituting the resulting Q conduction, the final linear algebraic equation that you obtained is shown here. Note that lambda is equal to 0 for explicit, lambda is equal to 1 for implicit, and lambda is equal to 0.5 for Crank-Nicolson. This is the final algebraic equation which is used, where you can see that temperature at P is a function of temperature at E, west, north, and south. And these are all the coefficient, as I mentioned earlier. This coefficient consists of two things: thermophysical property like K, rho, Cp, and geometrical parameter, which are like width of this control volume, surface area, volume of the control volume. Finally, I'll mention the, although the finite volume method is presented in all the books, various books on CFD, one of the most popular book in finite volume method is the classic book by Professor Patankar, which is now close to 40 years ago. He has written a very classic book where he had presented certain mathematical approximation. All this approximation which I am showing you is correct. This has been taken from his book. Note that here also the approximation is same. However, the way which I have presented the finite volume method, I had named it as a physical law based finite volume method, whereas the way he has presented and later on all the books in CFD have presented for is basically they start with partial differential equation. So I call their method like partial differential equation based finite volume method, whereas here I had presented, which I had proposed in my book for the first time in a CFD, what I call as physical law based finite volume method. Although the underlying mathematical approximation, the first approximation that I presented is stepwise, the second approximation that I presented is a piecewise linear. So all those approximations, since they are same, note that the final algebraic equation, whether you use physical law based finite volume method, which I presented here, or whether the earlier CFD book present the partial differential equation based finite volume method, both lead to the same algebraic formulations because the underlying approximations are same. I have discussed the explicit, implicit, and Crank-Nicolson method, where this explicit method is explicit and implicit are first order accurate, and the Crank-Nicolson is second order accurate. Note that the system of linear algebraic equation that that we derive here is very tailored to recursive computations, and we right now I have shown equations for only one of the representative yellow circle, and we use certain loops to solve for all the yellow circles, and it is tailored for recursive computations. With this, I had come to the end of this lecture. You can find the detail of this lecture in chapter 5 of this companion book, Introduction to Computational Fluid Dynamics. Thank you for your attention.